thank you for the Hagertys for having us here today. I'm really looking forward to have a look around the farm. It's been a long time since I've been out here and seen the progress. Also, thank you to DPIRD for putting today on, and it's a great crowd to see out here. So, what I'd like to talk about, firstly, I'm with a consulting company called Tierra Australia. We're currently a fairly small company. Some of you might know Peter Burgess, who set up and ran Calyx. So Peter's the CEO of the company and I'm working for them. So a lot of what we've been doing in recent times is looking at landscapes as natural systems and trying to figure out how we can restore natural functions to those landscapes. And so I'll give you some examples of the process that we follow. Okay. Not with that, I won't.
So it's there, so as long as you just keep clicking the right button.
Okay, so we've developed a process for looking at redesigning landscapes, looking by analysing as functioning catchments. We call it catchment function analysis. So the processes that the steps that we go through.
Sorry, Tim.
Okay, so is that better?
Yeah.
Okay. So we use a process of looking at landscapes and we analyse them as a functioning system, and I use Google Earth to do that. So we spend a lot of time on Google Earth and we're trying to figure out really how did that system function as a natural system before we cleared it. And we can map that out, look at the process and patterns of that. And so once we get an idea of how it used to function, then we can identify where those key processes have been interrupted. And I'll show you some examples of that later. Once we know where the key process has been disrupted, we can design interventions to restore those natural functions. That's basically what we're trying to do. We can then go out and implement those on the ground, and then finally we can monitor how they went. We learn, we do a lot of learning, and we can improve the system. So that really is the process of redesigning landscapes to restore natural functions. So this is an example of a catchment function analysis, a schematic. This is for the De Grey up in the Pilbara. But the patterns and processes you see here are really common. You'll find these in most landscapes. It's not identical to here, and every landscape is unique, but there are common sets of processes and patterns. So what we tend to see up in the top of the catchments, very often you'll get these fairly flat country high in the landscape, and that's not unusual in the sand plain, in the wheat belt where you get sands high in the landscape. In that landscape, and it's quite common but not so much out here, then you'll get a breakaway with the steep slopes, and you get a pattern where the creeks all come together. It's called a tributary pattern. So you've all seen that, creeks join up. As you move down the landscape, the slopes level out, and you'll get down to a point where it's what they call a petty plain, and you'll get main watercourses snaking across the landscape, meandering across it. And at the bottom, it can then, where it's even flatter, it can fan out again. And you'll get these alluvial fans. In the De Grey, then that drains into the main river channel. So it's a bit different here, but those patterns can be found here, and there's a few other ones. And then in this example, here's a catchment, a sub-catchment, highly degraded, a deeply incised creek goes through the whole system. Very dysfunctional, and basically the creek system becomes a drain that drains all the water away and dehydrates the landscape. The one on this side is healthier, and these red lines would indicate these are the critical components of the landscape. Because if they're functioning well, they'll store water high up in the landscape. And this schematic one, I said that one is really stuffed. There's a few places that aren't working well, we'd fix them up. And another critical one is these wetlands that are high in the landscape. So what we want to see with a hydrated landscape is fresh rainwater being held high in the landscape for longer. Where the system is not functioning well, we'll get drainage, and we're draining the fresh water out of the high country. And then down at the bottom, what we really want to see Often you get a tributary or you get a braided system, but we get wetlands all through that system, and they're really critical. And often they're the things that have been degraded. So hold the water high in the landscape for longer, and then have wetlands lower down in the landscape. It's a bit basic, but that's what landscape rehydration is about. So high in the landscape, one of the critical patterns is to see contours high in the landscape, and naturally they're built by water and litter and plants. Right, we tend to look at the landscape and think what with this shape of the landscape we see today is all due to underlying geology, and that does play a role, but a lot more than what we realise has actually been built by water working with litter and plants to build these patterns. So an example of that, I don't know if you can see it, but it's just a bit of bare soil, a little bit of a slope of terrain. The water's shooted down, carried the litter, and dropped the litter in level contours. That's the pattern that Mother Nature builds contours for us. This one, if you can see it, big rain in Perth, very flat country. The water's ponded, and then the litter is all floated off to the side, form that contour. That contour is perfectly level because the edge of the pond is perfectly level, and that litter contains seed. So the litter's dropped with seed in it, dung, the seed germinates, and then you'll get a hedgerow of plants. So these are small scale. These patterns are what are called fractals, and fractals are patterns that are repeated with it at different scales. Same pattern repeated within itself at different scales. So they're small patterns. Here's a really large pattern. I don't know if you can see it, but this is up in the East Pilbara, Ethel Creek, and you've got that drainage pattern of the creeks coming together, but between it you've got these level contours. So the water flows down there and is picked up behind these contours and distributed back out in the landscape. It doesn't all run down there. And unfortunately, that's how a lot of Australia used to work, a lot of those patterns that are struck. What are those patterns? They're actually mulga growths. We can see the remnants of those. It's actually difficult to find one now in Western Australia that's functioning really well. And another one, and I only ever saw this once, so this is up in the Pilbara, it's Mount Nameless, it's next to the mine at Tom Price. Every time there's a puff of smoke, the mine sends their fire brigades out and they put the fire out. So this is on the side of a steep hill, and it's not had, or hadn't had fire on it for decades. And so the spinifex is self-organised, basically like rice paddies. So these fill up with water when it rains. So if you get a cyclone drops 200 or 300 mils of water, you've got a chain of ponds down a very steep slope. So it's a step, it goes out, drops down like that. The water fills up that. Once it's full, it can overflow over the top of the spinifex or through it. So water is moving slowly down this landscape and safely. You know, the amount of energy of water is related to mass time velocity square. So if you slow water down, it loses a lot of energy, and if the water speeds up, it gains a lot of energy. So that was the only place I ever saw it, because it's the only place that's not getting the shit burned out of it in the rangelands, literally. But about 2 years ago, a fire did go through it. So you can see where the spinifex was. You probably might struggle to see it. Behind it was the terrace, but that is no longer functional. That was about this time of year, and then over summer we had the rain and washed all the topsoil away. It was destroyed because we lost the functioning patterns. That was the only one I ever found like that in the pool. Everything else looks like that. So how would you store all that landscape? Get on top of fire. Of course, farmers know about this and put contours into our landscape. So that's image from not that far east of here. I'm not sure whose farm it is, but exactly the same thing. So we can restore these patterns in the landscape to hold water high. Another critical pattern is what's called a chain of ponds. And that spinifex is a chain of ponds high in the landscape. The other one is low in the valley floors. So we want a chain of ponds, and they are built by water, plants and litter. So the water comes down, ponds out, drops the litter. You build up that lip, that raised lip, and the water will pond behind it. Then you get a lot of water comes down. When it hits that, spreads out, loses speed, loses energy, and deposits its sediments and nutrients and seed. So they were all through this landscape. This is how most of this landscape looked. We did not have incised creeks in most of the Australian landscape. It was this pattern. But our management has changed it. Erosion has started. It's cut up slope. As soon as it cuts through that nick at the bottom of the pond, you dehydrate that and it stops functioning. And then it gets worse and the erosion cuts all the way through it. So now we have a drain and it's dehydrating the landscape. That is what we see in the bulk of the continent today, unfortunately. So we can fix that if we plug the step. And by doing that, we can get really smart. We only need to do a little bit of work in targeted places and restore the natural functions, bring it back to that. One of the functions of that, well, there's that a pond, a chain of ponds does several things. One, it slows the water and holds it higher on the landscape. The other is vegetation grows in that. And these wetlands can then strip out nutrients, nitrogen, and they can take out between 40 and 90% of the nitrate in the water. And they'll take out phosphorus. And the phosphorus is carried, it doesn't get carried in the water, it's the sediments. So if the sediments drop out, we can hold phosphorus in these. And so at the bottom of these chain of ponds, you'll have clean water without high levels of nitrogen and phosphorus. And the other one would be agricultural chemicals. So these are critical functions of the landscape is to clean water up, because there's a consequence of discharging water down slope. So in terms of what we do, we try and we look at landscapes, try to restore them. This is west of Dandaragan, and it's a duplex, really gutless white sand, half a metre or a metre over clay. One rainfall event came off that hill and we had erosion creek form. Now that dropped the water table half to a metre lower, and it's drained all the soil out to the side. So we've gone in and rebuilt a chain of ponds back up the landscape out of white sand, which is fragile. So it's really critical we get the design right, and this one we did. So that had a big flow of water coming down and that sand held. Our Rotto Breeze, our farmer at Geraldton, has had 12 years experience learning how to do it, and he can get it right. So even though it's gutless white sand, if we get the shapes right, they will hold water. And the critical bit on that is that stone. That's what makes this thing stable. And the other critical bit about this is the level of that pond, that's the spillway around the side, is exactly the same at the bottom of the next step. We'll need to put a couple of small ones, so we've actually, when we get it right, the water ponds back to the next step, that ponds back to the next step.
How big is that?
That's probably about 4 or 5 metres wide. You can see the steel posts, and it's probably, I don't know, 10 metres long. So the flatter the land, the further apart these can be, and like with the spin effects where it's really steep, you have them closer together. We use different designs, and we also use leaky weirs, so rocks or logs so the water can slow down as it flows through, and we mix them up. There's a fair bit of this, and Rod's actually really good at designing this, so that we can, and the aim is to do as little work as possible. If we've got to do too much work, we haven't got the design right. And that's been proven. Our stuff-ups, when we push too much dirt, they blow out. Lots of little ones. So we're recreating that chain of ponds, restoring the natural functions that would have been there. Then on Rod's farm, when he bought it in about 12 years ago, that's what it looked like. He then went in and restored a chain of ponds and some contours coming out of it. That was 4 years later. That's the same spot. That's before and after looking up at the same hill. What was really interesting, he went and planted a few trees up there, but almost everything you see there was natural regeneration. So once we get the landscape functioning again, in this case we get the water functioning again and some ground cover, Mother Nature says, oh, I've been waiting for that for 100 years. That property's been farmed for over 100 years. and it pops up. And we're seeing this everywhere we do it, where we get it right, we get natural regeneration at no cost. So we're sort of lazy. We want to do as little as possible. We get this right, Mother Nature takes over and does the bulk of the work for free. And I think the Hagertys are seeing it on your place, where you sort of start to see this sort of thing. You're doing, your management is getting the system functioning again, and Mother Nature does it for you. Alright, so I've been having a look at this part of the world. So out here, this is pretty typical landscape out here. So you've got the rises with sands on the top of it and sloping down to the hollows, and you've got these broad flow lines through the bottom of the landscape, and you've got a chain of ponds. Oh, so that's what you want, a natural system. And the reason you've got a chain of ponds is there's these little rises between all those chains that are separating the ponds. That's really important. I don't fully understand it, but if you've got one pond and water sits there for a long time, you won't get a lot of plants growing up because it's waterlogged and not a lot of oxygen. But if you put a pond above it that are linked hydrologically, for some reason a lot more plants will grow in the lower ponds. I don't understand the science, I just know it happens. So having these ponds separated by these little sandy rises is critical to making this function. And the vegetation that grows on those rises is critical, because that's where the plants that grow there can strip out the nitrate. They can take out 40% of it really good, probably a system like that, 90%, almost all the nitrate. And agricultural chemicals, and also the phosphorus attached to the soil particle is going to get deposited. So it sort of doesn't matter what you're doing up here. If you've got a functioning chain of ponds, the water coming out of the bottom of this is pretty clean. But a little bit further west on the wheat belt, unfortunately that has been disrupted because because of management, we've had this erosion creep come the whole way through it. We no longer have a chain of ponds, it's all connected. We have a drain, and that's through, not here but further down, that's really common. So the chain of ponds is not functioning. So what I did is had a look at the Swan River system and mapped out where we've got a drain. So water that enters there, drains all the way into the Swan River. What was really interesting, I can see the old river going out there, that's the Moore River. You can see where the old river went. So that's the area that we get direct drainage into the Swan. This is where we've got a chain of ponds that's not directly connected. All right? So with your farming out here, your nutrients, probably agricultural chemicals, don't get in the Swan, but there they are. And so we could look at the catchment zones. So there's about 30% of the 11 million hectares is farms in the eastern wheat belt that are not hydrologically connected by surface flows into the Swan River. And the bulk of it is the wheat belt where you get direct flow that end up the Swan River. And you've got this tiny area down here as the Swan Coastal Plain, which is a small area, and the water, because it's gutless sand, the water will carry nutrients into the Swan. Why is this all important? When I was a kid, I'd go down Apricot Star with my cousin, we'd go swimming and fishing the Swan River. You can no longer do that. The Swan River is highly polluted through chemicals, but nitrogen and phosphorus, so we're getting algal blooms that are toxic. The Peel Inlet got worse, so much worse as when the algae bloomed and died, it stank so much that it was greatly devaluing all the high value real estate around the Peel Inlet, the canals and that. The Swan hasn't got to that. If it gets worse, and it does, the bulk of the political power in Australia, in West Australia, is now in the city. This is going to cause billions of dollars of loss of real estate in the city. So what the state government knows about this, what they've done is I think they've spent a couple $100 million cleaning up the septic tanks in the city. So they've greatly reduced the nutrient load going into the Swan from the Perth metropolitan area, but the problem is not getting better, and so the problem is coming from the wheat belt. We need to fix that. How do we fund it? What will it cost and how will we fund it? We've been, Tierra's been working on a new concept for funding landscape restoration with some partners, and we've been looking at rainforest in Borneo. But basically, what we're looking at is the landscape provides ecosystem services, your properties provide ecosystem services, and what ecosystem services are things that deliver benefits to people. Right? Yeah. And so they're clean air, food, water, clean air, and cultural and recreation values. So the services that's delivered by the capital, which is the natural capital, and we can put a dollar value on that natural capital. We're using a UN tool called TPIRD, which is the Economics Ecosystem Services, and we can say for a rainforest that's worth $5,000 a hectare in ecosystem services. Then we can use that natural capital to back a crypto coin. Bitcoin, who knows what Bitcoin's worth, because no one knows what it's worth because it's not got an asset behind it. We want to use natural capital to back an asset, a crypto coin asset, and raise the funds. We've been dreaming about this for 6 years. About 6 weeks ago, we signed our first contract. We now have the rights to 2.5 million hectares of rainforest in Borneo. And we're just working the process of getting a coin out there. As soon as we signed it, our backer came in with a big cheque. Our main financer, international group, has 18 months ago committed $100 billion to go into these sort of projects. $100 billion. The problem with that, it's not a problem any of us had, it's too big. So you can't go and say, look, I've got $1 million project, I've got a project with tens of millions of dollars. It's just, the guy running this hasn't got time. You need to go with projects with hundreds of billions or billions of dollars, and then he gets interested. So scale is important. My crude, rough estimate, it will take about $3 billion to restore the natural functions of the Swan River. And $3 billion gets the investor interested. It's getting to the scale that he needs to be able to make commercial projects. So the game, watch this space, the game is changing. We're saying there's opportunities in Australia. So just for Hagertys, quickly, we've done an analysis of that. We're sort of here, that's their property. This landscape is about some ridges running through it, sandy ridges sloping down into these lakes that actually don't connect to the Swan, and that's the elevation contour there. The other critical feature is these small sandy rises that separate the lakes. And Hagertys actually got very little erosion and very few cracks, so it says the system is working well. The water's not rushing off there, but over here we've got a system, a creek system that has insourced back up draining the landscape, and we could put in steps at critical places to restore the function of that. That's the sort of thing that we do. If we did that, then that's the area of land that could be rehydrated. So we're holding fresh water high in the landscape. Rainwater is fresh when it falls. We're putting water back in the landscape, then we need to use it. So this is here from Hagertys. This is a native perennial called Paspaldium that with their management just sprung back to life. Seed probably sitting there for decades. And that would tap in to use that extra water. I've seen feed quality of this, and this is as good as perennial ryegrass. This is Rolls-Royce quality feed. You just need to manage it right. Just a couple of things I want to talk about briefly before we go is, in terms of functioning systems, we're all concerned about climate change, and the planet might warm by 2 to 3 degrees by the end of the century. You can have a much bigger impact on temperature on your properties than that. So there's a site at Bibby Springs, west of Badgingarra, 20 k's from the coast. And I put an eye button out, little buttons that will record temperature every hour for 86 days, and I buried them just below the surface. So that's temperature, that's 65 up there, 11 down there, and the number of hours at that temperature. So where there was bare sand, we got up to 65 degrees. That's the purple line. And the lowest temperatures were there too. Where there was a good layer of litter, you might struggle to see it, we got up to 54, so almost 10 degrees cooler. But where we had perennial grasses, the green, we got up to about, I think it was about 45 was maximum temperature. On a neighbouring property, there was similar soil but had perched water, we had kikuyu, and that basically grew actively, or some was like subsurface irrigation, and that's the temperature profile. So a huge difference in temperature. In terms of the maximum, bare soil 65. We dropped to 10 degrees just having litter cover. 54, roach grass is 48, and where we had perennials actively growing all summer, 34 degrees. There were 440 hours of temperatures above 40 degrees on bare soils. We cook our soils every summer with our current farming systems, absolutely cook them, and the implications of that for biology, you're going to kill all your biology every summer. 440 hours above that, with good cover, a green leaf, it's never going to get too hot. I think this is a big reason why we're seeing improvements in soil fertility under perennials we've got green leaf, is temperature and its impact on soil biology. Finally, this is Benue, so right out northeastern wheat belt, and you can actually see the station country in the background. Green panic on yellow sand. What I did was I went out and took a sample within the green panic, so within the root zone, and then between it where there was no perennial, and compared those. And I'll show you the results. These are CSBP tests. Yellow sand, 21 parts per million P. That's not bad, and probably you guys have got similar soil tests. Alongside on the root grown, 71. I worked for CSBP and probably saw 7,000 soil test results. I never saw 71 parts per million P. Same soil type, same fertiliser history. The difference is a green plant with a living root compared to half the year everything's dead. Right? Nitrate and ammonia was no different, and that's pretty consistent. These perennial grasses are not putting nitrogen back into the system. I know about free-living rhizobia bacteria that fix nitrogen, but I believe you're going to have a nitrogen source in there. Bag fertiliser or legging, because you're not under perennial grasses building up your nitrogen. Organic carbon, 0.24 to 1.4, a four-fold increase in the organic carbon. Side by side, there's a four-year-old stand when I sampled it, a four-fold increase in organic carbon. Potassium, 44 to 150. Marginal deficient to, geez, that's more like clay. Sulphur, 2.7 to 7.9. The really interesting one, I didn't believe this. A few days before I got this, I went to Elaine Ingham seminar, and she said, if you get the biology right, your pH will increase and you won't need lime. Oh, yeah. And she explained it, but I was a bit sceptical. A few days later, I got the results. 5.8 without perennials, 7.1. She was right. So, in summary, what we need to do is hold water for longer in the landscape, use it higher in the landscape where it's fresh, clean up the water that does come down. And if we do that, if we integrate perennials into the system, so we've got green leaf, we'll cool the landscape, cool the soils, get the biology cranking up again, and get these amazing improvements in fertility. And it's good, the Hagertys has done it. So there's a whole pile of things we can do. One last one. This is up in the Benue. That's a green panic plant. These are wheat seedlings. You might struggle to see it, but there's a little one over here. I think where it is. Over there. About that big. That was the size of the wheat seedlings all between the perennials. This big sucker here, if you can pick it out, that's a wheat seedling growing in the root zone. So you head from that big to that big. The other interesting, and partly that's soil fertility, the other interesting things is these things harvest humidity out of the air, and in the dry times of the year, the soil in the root zone is wet or moist. And at the break of the season, the wettest soil is going to be in the root zone of perennials. Absolutely opposite to what I thought. So that suggests that we can pasture crop out here, and I think you've done a bit of it. finally, just so in terms of what we think we can do, we can use earthworks and good design to rehydrate the landscape. We need to increase the ground cover to reduce soil temperature. Use the extra water with perennials, doesn't really matter what they are, whether it's shrubs, trees, grasses, but green leaf all year round. And some of those trees we can make money out of, and then integrate it together in a mosaic of land uses. And each farm will be different, each farm will come up with a different solution. How do you integrate those things? And a really important one, I think, is how you integrate livestock back into the system. And there's really good opportunities to use things like sheep for in-crop weed control. And I've got a couple of farmer mates that are doing that. They're not using, well, they use some herbicides. They're using sheep to selectively graze weeds out of crops. And that becomes part of the whole system. So I actually think this is some exciting times again to restore the functions of our landscapes, make more money, and clean up other people's problems. Thanks.